This is our first lecture on frequency response, and frequency response has to do with looking at voltages and current um, in a circuit, an AC circuit, versus frequency instead of time. Up to this point, the voltages and currents that we've solved for have been with respect to time, but a lot of times it's necessary or advantageous to know how a voltage or current would change with frequency of a source. So this AC source over here, VI, has a frequency that can be varied, and often we want to see, well, how does the voltage and current in that circuit vary along with that source frequency? Now, there's what we call the frequency response equation, okay, which is symbolized with this HV of j omega. Okay, so this is frequency response equation. And there's various forms of frequency response equations with different quantities in a ratio like this. But the most common frequency response equation, and the one we're going to use in this class, is a ratio of V out to VI, where V out is the voltage across a load impedance. And the frequency response equation defined this way is just equal to the load impedance divided by the ZEQ of these two series impedances, or Z plus ZL. Now, from previous discussion, we know that the impedance of a resistor is just equal to its resistance. Impedance of an inductor is j omega L, and impedance of a capacitor is equal to minus j 1 over omega c. So what's important to understand from a conceptual point of view is that, remember that we talked about how impedance is opposition to AC current flow, and it's important to realize that the impedance of the capacitor and the inductor both depend on source frequency. The inductor impedance directly and the capacitor impedance indirectly. So as this source frequency is changing, the impedance of the storage elements is changing, but in a different fashion, in a different relationship. The impedance of a resistor doesn't depend on source frequency, so it's always going to have the same impedance regardless what the source frequency is at. But the fact that the impedance of an inductor and capacitor do change with source frequency is what allows us to design circuits that are called filters, where these filters will allow certain frequencies to progress from the input to the output while blocking other frequencies. And there's various types of filters. There's low pass filters, high pass filters, and bandpass filters. And in this course, we just cover in detail the bandpass filters. Now, once you understand one category of filter with very little added knowledge, you can analyze the other filters. And just because of the limited amount of time we have, we, in this course, as I mentioned, just cover the bandpass filters. So the first bandpass filter that we're going to look at is this one here. That's a series bandpass filter. Okay, so you'll see we'll look at two types of bandpass filters, the series case and also the parallel case later. Okay, this is a series bandpass filter. And you can see we've got our input voltage here, the output voltage is across the resistor, and then we have our storage elements. So we're going to start off by writing the frequency response equation for this bandpass filter. So HV j omega is just going to be the impedance of the resistor divided by the ZEQ, okay, which I'm going to write as R plus j omega L 1 over omega c. Okay, so this is our frequency response equation, and in this class we're interested primarily with the magnitude of this frequency response equation. So you see now we're going to look at the magnitude of this. Alright, so magnitude of HV j omega, well, magnitude of the numerator is just R, and then magnitude of the denominator is the magnitude of this complex number, so it's going to be square root R squared plus omega L minus 1 over omega C squared. So the next thing we're going to do is we're going to evaluate this magnitude of the frequency response for various omegas. And the first thing that would be useful to know is, well, when is the magnitude a maximum, right? Because when we have a maximum for our frequency response, okay, the magnitude of our frequency response, and remembering that this is equal to the ratio of V out over VI. Well, when this is a max, that means we have a maximum output. And a lot of times it's nice to know what frequency you get your maximum output at. So taking a look at this expression here, we would get a maximum magnitude when the terms inside this parentheses here would go away, right? Because if omega L, okay, if omega L is equal to 1 over omega C, well, this term goes away, right? Cancels here, and we would be left with that our frequency response, which is the same as our ratio of V out to V in, okay, the magnitude would just be R over the square root of R squared, okay, which is just going to be R over R, which is 1. Alright, so you see when the reactance, remember in an earlier video we talked about reactance, which is omega L, reactance of an inductor omega L, and reactance of the capacitor is 1 over omega C. Well, you see when the reactances are equal, when XL equals XC, that's when you get a maximum output. In fact, V out would equal VI in that case, and that's the most V out could ever be. V out could never exceed what the input voltage is. And the frequency at which this occurs is called the resonant frequency. And resonant frequency we symbolize a resonant frequency with omega 0. And if you would just solve for omega in this equality here, right, bring the omega up here, bring the L down here, then square root both sides, well, you come up with this expression for our resonant frequency. Oops. Let's start over again with that. Yeah, so resonant frequency 1 over the square root of LC. Okay? Now, it should be clear that if omega L doesn't equal 1 over omega C, well, then you're going to have some finite number here. So when you take the magnitude, that magnitude is going to be greater than R, the magnitude of R, so that we're going to get a ratio that's less than 1. So for any other frequency other than the resonant frequency, our magnitude of our frequency response equation, and therefore our magnitude of our output, is going to be less than what we have at the resonant frequency. You know, for example, if you were to plug in omega equal to 0, well, at omega equal to 0, which is DC, this term would become infinity, right? Because you'd have 0 minus infinity, so it'd actually be minus infinity. So going down here, you'd have minus infinity squared, which is just infinity, then R squared plus infinity, which is infinity, square root of infinity, which is infinity, and then R over infinity is 0. So you see at omega equal to 0, okay, we'll put up here, okay, when omega is equal to 0, well, that would lead to the frequency response equation magnitude equaling 0. And likewise, when omega is equal to infinity, again, you'd have infinity squared, then r squared plus infinity, which is infinity, then square root of infinity, which is infinity, then r over infinity, which is 0. So again, at omega equal to infinity, right, you'd get the same thing here. So if you were to plot the frequency response magnitude of our series bandpass filter over frequency, the source frequency, you would get something that looks like this. See, you would get a bell-shaped kind of curve where the max would be at the resonant frequency, and then on each side of that resonant frequency you get a slope. Now, in general, this curve is not symmetrical, but there is a special case where for all practical purposes you can call it symmetrical. But in general, the slope on the lower end of the resonant frequency is going to be steeper than what you have on the higher end. And we will talk about in the next video how we measure this type of response, and then how it fits into the name bandpass filter, what we mean by what frequencies get passed and which frequencies don't. We'll be able to tell pictorially by looking at this frequency response curve, this bell-shaped kind of curve in more detail.